Good morning. This is once more the IAA seminars. Today we will have a Severo Ochoa colloquia given by Dr. Marta Volonteri, titled Massive Black Hole Binaries in the Cosmos. And Marta will be introduced by the scientific director of Severo Ochoa program, Isabel Marquez. Please, Isabel.
Hello. Good morning, everybody. Thanks for coming to this online colloquia. It's a pleasure to have with us today Marta Volonteri. She's a directeur de recherche at the Institut Astrophysique de Paris, so belonging to the CNRS in France since 2012. Previously, she has worked as a researcher and professor at the University of California and the University of Michigan in the United States, and also at the Institute of Astronomy in Cambridge. She got a strong experience in teaching and also in supervising and mentoring students, with about a dozen undergraduate master students and a dozen PhDs and a 10th of postdocs. She has participated in several 10th international conferences organizing committees. She has been part of the board of the Groupement de Recherche Ondes Gravitationnelles, and she's member of the Conseil Scientifique de l'Institut, that I think it's translated as National Institute of Science of the Universe in France. She is also a member of the management committee, Cost Action, Gravitational Waves, Black Holes and Fundamental Physics, and co-chair of the LISA Consortium Astrophysics Working Group. She's a reviewer of the most prestigious publications in the world, like the Astrophysical Journal, the monthly notices, Astronomy Astrophysics, and Classic and Quantum Gravity, and also the most prestigious institutions like the Astronomical Society, the European Research Council, the National Science Foundation, the NASA, the Dutch Science Council, and so on. And she also serves the time allocation committees many times for Chandra, Magellan, and Subaru telescopes. Professor Volonteri has obtained several high standard fellowships during her career, like the NSF Astronomy Grant, a Marie Curie Career Integration Grant, several NASA NSF Chandra grants, and an ERC Consolidator grant. She's been professor by special appointment at the University of Amsterdam, and her work has several honors and major awards, like the NASA Theory Award and the Bloch Professorship at the Groningen University last year. She's interested in galaxy formation, the formation and evolution of massive black holes, accretion physics, stellar dynamics, and gravitational waves. And she has also performed observations of high redshift universe and active galactic nuclei. Her main research has led to the publication of more than 170 referred papers, 40 of them as first author, with more than 11,000 citations, age index 62 then. Today, Professor Volonteri will talk to us about massive black holes and binaries in the cosmos, as René said at the beginning. Thank you very much, Marta, for being with us, and enjoy her talk. That will be wonderful, I guess.
Thank you very much, Isabel and René, and I'm really very, very happy to be here with you. Well, not physically, but in some way to share some of my recent research with you. Today I will discuss some work that we have done recently on the evolution of massive black hole binaries in the cosmos, with an eye to making predictions for gravitational wave detections. And I just want to highlight here that this work is part of many, many years of work with many people, and in particular, in this case, by Hugo Pfister and Ricardo Beckman, who have been working with me on black hole dynamics and growth. So let me start with a brief introduction on what I'm going to talk about. So I talked about massive black hole binaries. So let me start with black holes and specifically defining what I mean by massive black holes. Generally, when we talk about black holes in the universe, we talk about two groups of black holes. Stellar mass black holes, notice here, these are just black holes, that the way I define it is that they have masses comparable to the mass of single stars in the universe. Masses from about a couple solar masses up to several tens of solar masses, with the record holder shown here on the right, the most massive and the most massive black holes ever detected in this mass range, announced by LIGO last week. The merger of two black holes that gave rise to the formation of a new black hole with a mass of about 150 solar masses. But then we move to another group of black holes. These are the black holes that I focused my research on, massive black holes. Here you have some examples. We have here M87, which is the central galaxy of the Virgo cluster. This galaxy has a black hole. You see here the jet coming from this black hole. You see a close-up image of this black hole from the Event Horizon Telescope. And we also have a massive black hole in our Milky Way. In fact, massive black holes are known because they power AGN and quasars. In fact, the first detection or discovery of massive black holes was from the discovery of quasars in 1963. They inhabit the center of many local galaxies. And in terms of mass range, observationally, for the moment, we have the lowest mass massive black hole currently observed is in NGC 205 with a mass of about 7,000 solar masses. And some of the most massive have masses in excess of 10 billion solar masses. An example here is Holmberg 15A with a mass of 4 billion solar masses. So you see here that currently observationally there is a gap between about 150 solar masses and almost 7,000 solar masses. I'm not going to discuss about that regime, and I will focus specifically on black holes that are in this massive regime. So something that we can associate to galaxy centers like Sagittarius A star, and associated to phenomena such as AGN and quasars. Going more in details about what I mean by active AGN, active galactic nuclei, and quasars. These are objects, these are sources, very bright sources that are powered by accretion onto massive black holes. This is the first quasar ever discovered, C273, discovered in 1963. And you see here that it's basically an object which is a point source. In fact, you have a large amount of light, about 10 to 11, luminosity comparable to the entire galaxy, but emitted by a region with the size of the solar system. So this points to a very efficient engine powering this object. And the only engine that has such power is a massive black hole with masses of millions to billions of solar masses. So here you have black holes of masses, or millions to billions of solar masses that produce enough luminosity to be comparable or more luminous than a normal galaxy. At the other extreme, we have what we call quiescent black holes. The best example is in the Milky Way, our own black hole called Sagittarius A star. It has a mass of 4 million solar masses, but its typical luminosity is about 10 to the 34 ergs per second. And you can compare this to the luminosity of the sun, which is about 4 times to the 33 ergs per second. So here you have a massive black hole that instead of being as luminous as the entire galaxy, is only as luminous as a single star. So you see here that there is a wide range of luminosities that are possible for a black hole. This luminosity is not produced by the black hole itself, by accretion of mass moving towards the black hole. So it's conversion of rest mass energy as this mass flows in and eventually disappears into the black hole. To put this in a more global context, I mean, what I actually do is to study the evolution of black holes in a full cosmological context. So black holes in galaxies. So what is the link between massive black holes and galaxies? I said galaxy like the Milky Way has a black hole in the center. M87, so the central galaxy of a galaxy cluster has a black hole in the center. And if you look at the mass of these black holes, a function of the mass of the galaxy hosting them, you see that the most massive galaxies host the most massive black holes. And as you go down to low mass galaxies, the masses of the black holes also decrease. Overall, you can think, as a rule of thumb, that the mass of a black hole in a galaxy is a fraction of about 10 to the minus 3 to 10 to the minus 4, the mass of the galaxy, well, up to 100, up to 10 to the minus 2 at the most massive end. But the main point here is that black holes and galaxies know about each other. Small galaxies host small black holes, and large galaxies, large black holes. So their evolution is connected over cosmic time. So to put this in a better context and give a glimpse of why our work is not super easy, let's not talk only about mass scales, but also physical scales. Here I have some conversions of units in case some of you are more familiar with physics than astrophysics, but probably this is not the crowd that needs this, but in any case it's there. Now let's think of a galaxy. Let's take the Milky Way as an example, or a Milky Way-like galaxy. A galaxy is typically composed of several things. Let's start with the dark matter halo, with a mass about, say, 10 to the 12 solar masses, and the physical size about 100 kiloparsecs. Then we have the visible part of the galaxy, stars and gas and a disk and a bulge, with a mass that is usually about 10 to 100 times smaller, and a physical scale that, in our case, about 10 kiloparsecs. So again, a factor of 10 less. Now let's put a black hole there with a mass of about 1,000th of the mass of the galaxy. And all of a sudden we see that this black hole is characterized by scales that are much, much, much smaller. There is a region called the boundary radius, which determines the radius within which gas is bound to the black hole, so it's energetically bound to the black hole. And you can define the same for the region where stars are bound to the black hole. This is called sphere of influence. And both of them have sizes of about parsec scale. So you see that we go already a factor of 10 to the 4 smaller than the visible size of a galaxy. Not to mention the Schwarzschild radius, which has the scales of microparsecs. So it's really, it's very, very small dot in the middle of the galaxy. So if you want to study black holes in galaxies, you're faced with the challenge of the scales that you have to study. We do not have a single approach that can connect from the Schwarzschild radius, where general relativity dominates, to the scales of the entire galaxy, where we usually use Newtonian physics, but then you have a star formation and much more taking place. So we usually use different techniques on different scales, and I specifically focus on the large scale structure around black holes. Moving on to why I like binary black holes. The reason is that binary black holes are the strongest source of gravitational waves in the universe. We know that because LIGO has seen plenty of them. LIGO Virgo in the last few years have detected plenty of binary black hole mergers. But an important point is that massive black holes, those that I work on, are not sources that we can detect with LIGO and Virgo. The reason is shown in this simple equation here. You have a binary of black holes, the binary shrinks, the black holes get closer and closer until eventually they merge. At the moment when the two black holes merge, are separated by about their respective Schwarzschild radii, and they move at the speed of light. So you can transform these into a typical frequency at which merging black holes will emit gravitational waves. And since the Schwarzschild radius depends only on the speed of light and the mass of the black hole, you can easily show that the frequency is inversely proportional to the mass of the black hole. Now, if you take a black hole with a mass of, say, 10 solar masses, the frequency is about 1,000 hertz, and this is what LIGO Virgo can see. But if you go to more massive black holes, say 10 to the 6 solar masses, the frequency becomes about millihertz, much smaller. Now, since if you need to detect this, you need an interferometer. An interferometer must have a length, a size, comparable to the wavelength that you want to detect. So if you're going to lower frequency, you need a larger arm length. And in particular, LISA can detect black holes with masses about 10 million solar masses or so, between 10 to the 4 and 10 to the 7, but it needs an arm length of about millions of kilometers, and so that's why it's a satellite in space. Then you can go to even more massive black holes, about billions solar masses. In this case, the frequency will be about a nanohertz. In this case, you need to detect waves with this frequency, you need an interferometer with the size of pretty much inside the entire galaxy. And this is actually an experiment that is currently taking place, and it's called partial timing arrays, where they use the time of arrival of different pulses to see if over the whole galaxy there was a perturbation in space-time that changed the arrival of times of pulsars. And so the basic point here is that different families of black holes of different masses emit in different frequencies, and these can be detected with different instruments. And I will focus here on the more massive black holes. So LISA, the satellite in space, it's an ESA NASA mission, and pulsar timing arrays, this galaxy-wide interferometer. When we look at the evolution of black holes over cosmic time, as I said, black holes evolved with galaxies. They start small and they become larger. And then as they grow in mass through accreting gas when they are quasars. You know, there is just some mass that crosses the event horizon and goes into the black hole, or by merging with other black holes. So in this figure shows redshift or time, cosmic time. We are here today, and this is early cosmic times. And here you have mass of black holes. Each of these curves shows the growth in mass of some black holes. Let's look at, for instance, red black hole over here. It's a black hole that is born when the universe was about 300 million years. And then it grows here by accreting gas. And then here you see it jumps in mass because it merges with another black hole. And then accretes, merge, and so on and so forth. So this is the whole cosmic history of black holes. Black holes, and in all these, black holes grow with galaxies. Now, look at this shaded area. This shaded area shows the detectability of black hole mergers, so each of these dots, by the satellite LISA. What this tells you is that pretty much any black hole with mass, say, between 10 to the 5 and 10 to the 7 can be detected in the universe with this satellite. Then if we move towards later cosmic time and larger masses, this gray area shows what we can detect with electromagnetic probes, our telescopes, that's it, with photons. You know, for instance, JWST or LINX, these future missions can see small black holes up to high redshift. And then the most massive black holes can be detected by pulsar timing arrays. So all in all, using different probes, gravitational waves, photons, telescopes, we can really track the growth of black holes over cosmic time for the whole history of the universe and galaxies. So what I've been trying to do in the last few years was really to put this, you know, all this together and try to see, to make predictions for what we can see with this approach. Oops. My favorite movie, is it working? No movie, I'm really sorry. Let me try once again. Well, during question time, I will try to have it again. But what I wanted to show you with this movie was the evolution of a galaxy with its black holes, to really show you how we have to connect these many scales if we want to understand the physics of black holes. In particular, if we want to study black hole binaries that will eventually merge and emit gravitational waves, we have to study this in a cosmological context, taking large-scale structure into account, because it's cosmology and large-scale structure that tells us what is the merger rate of galaxies. And since black holes are inside galaxies, the merger rate of galaxies is the starting point to look at the mergers of black holes. So here we move to smaller scales when two galaxies merge. So basically, in a full cosmological context, you can see hundreds of thousands of interactions and mergers between galaxies. And in this case, if we imagine that there are two black holes at the center of this galaxy, eventually they will find themselves at the center of the merger remnant. And what will happen is that if there are favorable conditions, the black holes will form a bound binary. Now, this happens after the galaxies have already merged, in the sense that galaxy mergers need to be supplemented with additional physics in order to understand and study black hole mergers. When the galaxies are separated by about 1 kiloparsec, they form a new galaxy. That's it, it's done. But for black holes, when they're separated by 1 kiloparsec, we're just the beginning of their evolution. When they're separated by 1 kiloparsec, there's just two black holes. They're not a binary of black holes. They form a binary at parsec scales through a physical process called dynamical friction. Then suppose now that these black holes are separated by 1 parsec. They're still very far away from where they meet gravitational waves, which is about milliparsec. So they still have to cover 3 orders of magnitude. And this is through physical process that have to do with torques in gas disks and stellar scattering. The main point here, really what I wanted to show, is that to study the problem of the formation of massive black hole binaries and then their mergers for gravitational waves, you need to connect scales of hundreds of megaparsec in cosmology all the way to sub-parsec scales. This is a long journey, both in terms of space and time. And so that's why we have been working on this since 1980, and many of these issues are not clear yet. So now, suppose that you want now to study massive black hole mergers in the universe and understand what gravitational waves will see and tell us, and couple that to telescopes. What do you need to start? I mean, what is the recipe book? Well, first you need lots of galaxy mergers, which means that you need to sample the large scale structure of the universe. And you need a statistical sample. So you need the large volume of the universe that you can simulate, so that you can have a statistical sample of many galaxies, many black holes, many mergers. However, I just showed you that black holes merge on very, very small physical scales. So you need very high resolution to actually track the kinematics and the dynamics of stars and gas and black holes all the way to where they form a binary. We also need a variety of galaxies. The massive black holes that host the massive galaxies that host the most massive black holes that we can see with pulsar time arrays, and dwarf galaxies that can see the low mass black holes that we can see with laser. But this is rather challenging because in case you're not a theorist working on simulations but an observer, you can make a simple analogy with observational surveys. You can have either a large and shallow survey, say like SDSS, where you have a large fraction of the sky, but not a very high depth. In analogy with cosmological simulations, this would be a simulation with a large volume, many objects, but a low resolution. And this will allow you to study only massive galaxies. Or you can have a pencil beam survey, something small and deep, like the chandelier itself, for instance, or candles. The analogy in cosmological simulations is something that has a small volume, therefore few objects, but it has high resolution, and then you can study dwarf galaxies. So this is, in some sense, the dichotomy, the difficulty that we are faced at the moment. We need what we cannot have. So instead of giving up, what I decided to do was to use a mixed approach. In particular, I took a large-scale simulation. You have probably heard of these large simulations like the Illustrious, Eagle, Massive Black, or Horizon AGN, which is the simulation that I use. These are simulations that are very large volume, but relatively low resolution. So if I show an example here with our simulation, again, they're all very similar in terms of properties. You can resolve dark matter halos with a mass of about 10 to the 10 solar masses, which means that the galaxies that you resolve are also relatively massive. And the physical resolution is about 1 kiloparsec. So this is very far from when black holes emerge. So you have access to this simulation, which is okay to study massive galaxies, and so probably well, black holes for pulsar timing arrays, but not for LISA. What can you do if you want to study LISA? You can use a smaller simulation, but with a very, very high resolution. This is a very new simulation. It's called New Horizon. It shows here, it takes a sphere in the middle of the other simulation of Horizon AGN, and it resimulated at higher and higher resolution until we reach about 40 parsecs. Now, this is really high resolution for a cosmological simulation with this volume, because this is a volume of more than 4,000 megaparsecs. So with this simulation, we can actually track dwarf galaxies and the black holes in them. In case there are some people here interested in the details of the simulation, it's a sphere of 10 megaparsec radius. We can resolve galaxies down to about 10 to the 6 solar masses, so really, really dwarf galaxies. And we study, and we have black hole physics, accretion, feedback, dynamical friction from gas. I will go back to this. And we also have spin evolution in case this is something that you are interested in too. So at this point, we have these two simulations that cover the range that we're interested in, although they're not connected. And so we can start making some studies. Now, this is just a series of pretty pictures of galaxies from New Horizon, where I would say that produce galaxies that are really very realistic, both face-on and edge-on, with dust lanes and very well developed disks. Let me just skip this, but it's just to show the difference between having a low resolution simulation and a higher resolution simulation. You can really see all the kinematical details of the galaxy, and so you can really track the gas also going near the black hole. So this is the starting point. We have two simulations. One that reproduces massive galaxies. This is the galaxy mass function of a Horizon AGN, shown here in gray, with a bunch of different observational results. This is a thrashing point 4. And you see here that Horizon AGN can track galaxies with mass 10 to the 9 and higher, up to 10 to the 12. And then we have New Horizon that can track low mass galaxies down to 10 to 6, 10 to 7 solar masses. But the volume is sufficiently large that we have many of these dwarf galaxies, but it's not large enough that we can have these rare, very, very massive ones. So we'll use Horizon AGN for massive galaxies and high mass black holes, for pulsar timing arrays, and New Horizon for dwarf galaxies and low mass black holes. Just to highlight that this is indeed the case, this is the mass distribution of all the black hole mergers that I track in New Horizon and Horizon AGN. And you see here that really they cover the range of frequencies that LISA can detect black holes in, or pulsar timing arrays. So our bet that these black holes would be well described by this simulation was actually correct. Oh, and I forgot to say, this is some work that I actually led this year. It's my first author paper in 4 years, so it's been a while since I've been writing the paper, but you can find more details there. So going forward with this, let me go back to the physics, which is actually my favorite part. Here with this slide, I already showed you that, I told you that the physics of massive black hole mergers is very complex because it includes physics that is not necessary to study galaxy mergers. In particular, you see here these two parts: dynamical friction, gas torques, and stellar scatterings. These are all processes that act on the black holes to make them merge, but they operate, as you see here, on very small scales less than a parsec. So in a simulation, even with a high resolution like New Horizon, which is 40 parsecs or 35 or 40 parsecs, we still cannot track all of this. We can track only part of this. So we really have to compensate by adding, these phenomena in post-processing. Let me just here give you a glimpse of what I mean by dynamical friction. If you remember your galactic dynamics, the dynamical friction is the deceleration, the friction that occurs when a perturbed body is moving in a distribution of other bodies, less massive typically. If this body, the perturber, is moving with a net velocity in a given direction, it will exert a force, and you will get a force back on the other particles. In practice, what happens is that for the other particles, the other stars or gas or whatever you have, the velocities in the tangential direction will cancel, but the velocities in the radial direction will not cancel out when you calculate all the long-range interactions. And if velocities don't cancel out, they give rise to a net force acting on the particles and on the perturbers as well. And the way this force acts is to slow down this perturber. And the equation is shown here. But notice here, you see that these are the particles that slow down the black hole, they wake, and these particles that slow down the black holes the most will be those very close to the black hole. How close? Close means within what we call the deflection radius, which for a black hole of mass 10 to the 7 solar masses is about 1 parsec. So it's very, very tiny sphere. It's something that, again, with the resolution of cosmological simulation, we cannot track. So we have basically you are underestimating the force, and so you have to compensate in post-processing for the dynamical friction that you don't have when the black holes go below 35 parsecs. In a similar way, you also compensate for the other physical processes that have to do with black holes and not with galaxies, and occurs on sub-parsec scales. So once the binary forms, it interacts with other stars, single stars, or evolves with torus in a disk. And so these are all processes that can be described analytically, and you can add to your analysis of the simulation in post-processing. What happens when you do that? So you take all these equations, I mean, they're all very simple, and you calculate dynamical friction timescales, you calculate all the timescales for all these processes for all the black holes in your simulation. And this is what you get. So here, as a function of the galaxy hosting the black holes, I show you here this delay time that you calculate in post-processing to be added to the simulation. I don't want to go into details, but just look at here. So this arrow in green shows a time of about 10 billion years. So the age of the universe, give or take a few billion years. And you see here, these delays can be very, very long. So in some sense, if in your analysis you forget to include all these processes that are specific to black holes, you will severely underestimate the time it takes for the dynamic evolution. So it's a very important process. So now, what happens when you correct your simulation for this? Now, this figure shows you the merger rate of black holes. This is what our instruments can see. This is shown from the horizon AGN, meaning that this is the merger rate of massive black holes for pulsar timing arrays. This is the raw merger rate that I get from the simulation. And then once I correct for these delays, you see that fewer black holes are actually merging. This is because for some of these black holes that appear to be merging, the delay time can be 10 to the 4 gigayears. So they will never merge. And so they cannot actually account for sources of gravitational waves. And the same here is for the other simulation, New Horizon, the one that tracks dwarf galaxies, dwarf black holes. And so it's perfect for studying black holes for LISA. And you see again that you have the initial merger rate, and then as you correct for more refined time scales, the merger rate decreases, but it never goes below 1 per year. Now, this is a lower limit. I'm not going to explain why, but the most important point here that I want to make is that if you do not want to really underestimate the merger rate of black holes, you need a higher resolution simulation like New Horizon. Because as you see here, the merger rate is much higher in this small, tiny volume of the universe than in Horizon Again, that has a large volume of the universe. Why is that? It's very simple. It's just, you know, the basic evolution of galaxies. The galaxy mass function is a steep function, so that you have many more dwarf galaxies than massive ones. So in the same way, if you can resolve dwarf galaxies, we will have many more galaxies in a given volume, and you will have a higher merger rate. But this is not the whole story. There are many people, even today, doubt that dwarf galaxies host black holes. Now, if you have dwarf galaxies, you can resolve all of them in your simulation, but these dwarf galaxies have no black holes in them. Then you have lots of galaxy mergers, but 0 black hole mergers. It's important, if you want to understand black holes in dwarf galaxies, to ensure that we do have black holes there. Observations say that about 10 to 50% of dwarf galaxies should have black holes. And indeed, in the simulation, we also confirm that we do have black holes in dwarf galaxies. So when 2 dwarf galaxies merge, you do have a non-zero probability that you will have a black hole merger as well. So in summary, resolving dwarf galaxies is really crucial for low mass black holes, especially those that we want to detect with LISA. The next question that I asked myself, I mean, seriously, these are questions that I've been playing with or toying with since my PhD. And for the first time ever, I had these simulations that could actually work on these questions. So for me, it was just, like, it being in a playground. So now what I wanted to know, and what I hope other people are interested into, is what galaxy mergers do form black hole mergers. Now, the rule of thumb that you derive from analytical calculations or from simulations of isolated galaxies is that you need a mass ratio larger than 1 to 4 for the galaxy mergers to obtain a black hole merger. This has to do with the efficiency of dynamical friction, with tidal stripping, tidal shocks, and so on and so forth. Again, I can discuss all this if you want to have more details. Well, it turns out that if you are in a cosmological simulation, when you have a large variety of galaxies with different mass ratios, different orbital parameters, where you really cover a wide range of properties, this simple picture is not true anymore, in the sense that you have some galaxy mergers with relatively low mass ratios that still create black hole mergers. This can be shown in this plot. In this panel, I show the mass ratio of the merging galaxies. Black is the full population of the simulation. This is Horizon Again, New Horizon. It doesn't really matter. Let's focus on this one only. And then in blue, I show the distribution of galaxy mergers that generate a black hole merger. So you see that clearly there is a bias in terms of merger rate of mass ratios. Very, very low mass ratios. So when you have a small satellite in the large galaxy, it is true they do not lead to a black hole merger. If you have a mass ratio larger than 0.1, or between 0.1 and 1, this is the best situation. But there are also some minor mergers that still contribute. So to me, this was very interesting. And again, this has to do with the power of having cosmological simulations where you could track a large variety of environments. This just highlights this point, but makes another one. So now you're an observer. You catch two galaxies in interaction, merging. Can you predict or can you guess if this will be giving rise to a black hole merger? Statistically, you can. this is exactly what we have done here. So here you have the mass of a galaxy. And then for each merger that has a galaxy in this mass bin with different mass ratios, 0 to 1/4, 1/4 to 2.5, half to 3/4, 3/4 to 1. So these are minor mergers, these are major mergers. What is the probability that after this galaxy merger, you have a black hole merger? You see here that for small galaxies and low mass ratios, this probability is relatively small, about 10%, which is not super small, but still small. And then it climbs up and goes close to unity for high mass ratio and high masses. But overall, if you take this and integrate this, you find that only about between 5 and 15% of all galaxy mergers lead to a black hole merger. This is because of the reasons that I've already discussed. In some cases, only one galaxy hosts a black hole. In some cases, none host a black hole. So just have a galaxy merger, but no black holes there. And in some cases, just ineffective dynamics. Again, depending on the orbital parameters, depending on how fluffy or dense your galaxy is, you may or may not have that the galaxy merger leads to black hole merger. So this has a direct consequence in the sense that if you have mergers with black holes, but with ineffective dynamics, so there will be a population of black holes that are not merged, that are wandering in galactic halos, in galactic disks, and are just the leftover population of a sequence of mergers that have not led to a black hole merger. If I can show you the movie later, this is much clearer. But this is an example from a paper by Michael Tremel in 2018, where you see here a Milky Way galaxy with its central black hole. So this will be the analog of Sagittarius A star. But then you have here, in this case, 1, 2, 3, 4, 5 black holes that are just wandering around, and they were left over from failed mergers. And again, this is a very classic prediction of basically all models that do this in a cosmological setting. So this brings me to the very last question that I want to address. I hope that I'm right about this, the correct timing, which I think is the most interesting for people who want to chase black hole mergers using telescopes, which is, how can we identify the galaxy where black holes merge? Many people used to tell me, oh, well, we just look for merging galaxies. If you have merging galaxies, you have merging black holes. But as I just explained to you, the black hole mergers take much longer than galaxy mergers. So no, generally merging black holes are not found in merging galaxies. This is an example. In this figure, I show you the delay between the time of the galaxy merger and the time when the black holes merge. This is a relatively busy plot, but the point here is that the delay between the galaxy merger and the black hole merger can be generally longer than 1 gigayear, up to 10 gigayears. So if it takes 10 gigayears for the black holes to merge after the galaxy merger, the galaxy has relaxed. Now, this is not totally true because we're in a cosmological context. So galaxies after this initial merger will have many more mergers, but this will not be related to the initial point. So you may have that black holes merge in a merging galaxy, but that will be total chance. It will not be related to the physics that created the binary. These are just some examples, some pretty pictures of black hole mergers from galaxy mergers, just to show you the evolution of the galaxy over time. So this is the galaxy merger. You see, these are two black holes. You see them here, these two red dots. This is a galaxy merger between two galaxies mass 2 billion and 10 billion, and 10 billion solar masses at redshift about 3. You see here, this is a very messy situation as expected. Then we go to this time. So the simulation tells us that black holes should merge at redshift about 1, when the galaxy is kind of messy, but definitely not something that relates to this merger. Now, as I told you, the simulation does require some post-processing and addition of these black hole specific timescales, which you do add, and then you get to this point. So the black holes that started interacting at redshift 3.2 merge at redshift about 0.6. You know, this is about 6 gigayears later. So the galaxy that here were small galaxy has grown to about almost more than 10 to the 10, so our mass is 7 times 10 to the 10, and it's just a normal quiescent dusty disk. This is another case. I particularly like this one because it looks at dwarf galaxies. This is another sequence that starts at redshift higher than 7 with these two black holes and these two tiny dwarf high redshift star-forming galaxies. Probably know those that contributed to realization. But then by the time the black holes merge, it's several gigayears later. It's about 2 gigayears later. So again, in this case, you have a messy galaxy, but this is because you're talking about higher redshift universe. In the higher redshift universe, everything is a bit of a mess. But it's not because of this merger that happened 2 billion years ago. So it's conceptually very important if you want to understand the physics behind black hole mergers rather than just randomly select galaxies. So this brings me to my conclusions, my summary. I hope I got you a little bit excited about black hole mergers and gravitational waves, all these in a cosmological context. It is a bit messy, it's true, but then there are so many unanswered questions that it's just a lot of fun to work on it. I just want to stress here that it is very important to understand that to track black hole mergers in a cosmological context, we need to be very careful about the way we treat our analysis. And that we're really at the start of a time when we can do this both observationally and theoretically together. And I hope that some of you will work on this as well. Thank you very much. I will stop here.
Thank you very much, Marta. Perfect, on time. Don't need to tell you about the time. So for the audience, anyone that want to ask a question, please raise your hand and I will give you the micro. So we have two here, Isabel and then Jorge Sanchez. Please, Isabel.
Okay, thank you. I was going to say that Jorge first. But anyway, Marta, thank you very much. It has been a very, very nice talk. And I have a comment and a question or 2 comments or whatever. When you've shown just 2, 3 slides before the merger of galaxies with black holes, you showed a picture where we saw 3 galaxies. So, but I had understood that you were dealing with mergers of 2 galaxies, right?
Yes. So this, yeah. So this is well, in this case there are 3. In fact, there are several black holes in there. So in this particular merger, there are 3. So there is another black hole there. So here I followed. Here I just show in this picture the merger of these 2 black holes, but there is another black hole in this galaxy, and in the paper I show the evolution of the other merger as well. So you can have cases where a single galaxy merger can eventually produce multiple black hole mergers if there are multiple galaxies involved or multiple black holes.
Yeah, but I mean, the question was more related to the fact that when you put more and more galaxies, the parameter space broadens. So I guess it's much more difficult to get the results, right? So,
well, it's a cosmological simulation. So you just have whatever parameters that the universe gives you.
Yeah.
It is true, however, so here I focused on what I call macroscopical parameters, basically masses. But in reality, there are other parameters that are very important, but that, for instance, in observations, we cannot easily measure. For instance, the compactness of a galaxy is one of the most important parameters. But this is not something that is easily obtainable in observations for a large sample. So that's why I focus here on, you have a large statistical sample, but then from that parameter space, I reduced it to a small fraction. So basically masses and mass ratios and redshifts. But yes, orbital parameters, density profiles, these are very important as well.
Okay, so I think if I've well understood, the takeaway message is then when you try to deal with the observations of the present day universe or at whatever redshift and the eventual origin of the black hole that you have now from a previous merger in the past history, as that you mainly don't know, right?
Yeah, it's yeah.
So what kind of experiment could you propose to search for? Because there are many works dealing with double-peaked, for instance, spectroscopic AGN and things like that, just trying to get a hint of the history of AGN.
Exactly.
So what's the conclusion from that? I mean,
well, no. Okay. So when we talked about black hole specific signatures, such as double-peaked lines or velocity shifts, these are still fine. What we should not do is to look only in interacting galaxies, because my expectation is that most black holes that are close to merger will not be in this type of galaxies, but in something like this. So it's more about, but then yes, absolutely, I agree with you. Then if you need actually to see the black hole, I mean the black holes themselves, then you have to look at black hole signatures. Shifted broad lines, double peak broad lines, that is usually the ideal way, although there are very many false positives. And then in X-rays, you can also find the two sources, but yeah, I agree with you that then you need additional tools.
Okay, thank you. And the comment is that I love your simulated galaxies.
Oh,
with galaxies like these, we don't need any telescopes, right? Joking. Okay, thanks a lot.
Okay, we have two more questions, one from Jorge, then Almudena Prieto. Please, Jorge.
Okay, first of all, I mean, thanks for the talk. Very, very interesting. It's actually a double question. The first one is about the seed black holes that you inject to zero in the simulation. And then, if I got the message right, most of the black holes never merge within the edge of the universe. So they are just wandering around. Can you comment on how can we detect them? Not the ones that are not in the possibly merged, but those that are wandering, that will never merge within the edge of the universe.
Okay, I'm afraid that I couldn't hear 90%.
Okay,
I
heard
and failed mergers.
So I will start again. First is about the seed black holes that you inject in the simulation. So, and the second is about whether most of the black hole never merge within the edge of the universe. So, any idea how can we detect them?
Okay, so first about seeds. The seeds in the simulation are forming in dense gas cells. So they're based on, they're not based on halo mass, but just when you have conditions where the cell would collapse into a massive star, and then we put a black hole there. And the initial mass is 10^4 solar masses in horizon and 10^5 solar masses in horizon AGN. So they're not following specifically a low metal listing model, if you are asking for that, but at least the seed formation model is based on local gas conditions and not just a mass threshold. Then if most black holes do not merge in the universe, so from what I've seen doing this analysis and some other work, most black holes actually do merge in the universe, or they experience at least one merger. So this was the first part. So in general, yes, most black holes experience at least one merger in their lifetime. And of course, this number increases if you go to more massive black holes in more massive galaxies. And then I think the last part was how to detect failed mergers.
Yeah. No, not failed mergers.
I don't
know. Black holes that are wandering.
Black holes that are?
Wandering. I mean, those that are not.
Yeah. So yeah, what are the possibilities to detect these black holes? Basically, it's not very easy in the sense that the luminosities that you predict for these objects are very small. This is work that I've done a long time ago, so I don't remember on top of my head, but they were below the typical luminosity of ultraluminous X-ray sources, so that gives you a range. I think it was something like 10 to 38 ergs per second by accretion from an interstellar medium, or on the other hand, the probability that one of these black holes captures a star passing through the disk is super tiny. So accretion is not very good. There is some probability with microlensing, but you have to be very lucky. In terms of looking at microlensing match style, this is probably not feasible for wandering black holes with mass larger than 100 solar masses because the period would be too long. So in summary, it's very hard to see them. Otherwise, probably we would have seen many more. We have some candidates, by the way, but as usual, they remain candidates.
So thank you.
Thank you. There is one more question by Almudena Prieto, please.
Good morning. You hear me?
Yeah.
Okay. Thank you for the talk. Very nice. I just wanted to put forward the fact that the observational evidence of this merging black hole is very small, and not because we don't have the means now to look for them, at least for the very nearby universe. And we have the scales to do so, and we look for objects that are pretty good candidates for having it and don't found. So the statistics is small, very small. And we survey from early type objects like Centaurus A or M87, and we can go to Andromeda, different type of galaxy, lower black hole mass, to our own Milky Way. So maybe there is a fact that the statistics is small as evidence in our near universe. Maybe the detection of these black holes, because they kick out to each other, maybe the other black hole is somewhere in the galaxy, then becomes very hard to find it, because might be no accreting, so we don't see it unless we go dynamically in a place to look at it. But I don't know if that fits where you're modeling in your prediction, because the reality is not very favorable.
Well, no, actually predictions predict very few of these black holes. So both in terms of binaries, so in terms, I have only a couple of papers on this, but the prediction on the detectability of binary black holes, either through velocity shifts in the broad lines, or through shocks or different phenomena. So I wrote a paper back in 2008, I think, on double broad lines, and last year with Julian Krolik, a paper on shocks and different temperature signatures of binaries. And we're predicting basically that at the moment, the observations are well within the predictions, in the sense that the predictions are still below the number of observations. The only case, so I've never worked on periodic binaries. I know that Luke Kelly and Alberto Cesana have, and they have compared to some work done by Graham et al. With the Zwicky transient factory, and look at PTA. So there is some tension there. So if all the binaries found by the Zwicky transient factory are indeed binaries that can be detected by PTA, then this is in tension. But otherwise, everything, I mean, the basic point is that the number of binaries that we predict, that we can see at any given time, is very small. So I don't have the numbers on top of my head, but I can send you the references to these papers. In terms of wandering black holes, again, the luminosities that are predicted are so low that I think at the moment we're way within the predictions, unfortunately. On the other hand, if we were not matching the observations, I would have thrown away this simulation. So. And to me, a theoretical model that does not match the universe is wrong. Like, that's it.
Okay, thank you. Any other question for Marta? Here is one more by Anchon, please.
Hello, how are you? It was, thanks Marta, it was a very nice talk. Thanks a lot, I have enjoyed it very much. I wanted just to mention the role that SKA can play also in the detection of very low frequency gravitational waves. Besides the pulsar timing array that you have mentioned in your slide, I think SKA can be in the next years a very key element in the detection of these very low frequency gravitational waves.
Absolutely. I mean, SKA will be way beyond anything that we have now.
Yes, essentially, yeah, because you have the possibility to detect many more millisecond pulsars with precisions of hundreds of nanoseconds in periods of some tens of days. Then really it will be an extremely sensitive instrument to detect small space-time perturbations, especially coming from those supermassive black holes, I think.
So yes, no, I'm with you.
Okay, thanks a lot for your talk.
Thank you.
Thank you. Any other question for Marta? Okay, seems there is no more question. Thank a lot, Marta, for this very nice talk, very nice, interesting talk. I think we can.
Rene, I would just wanted to acknowledge again, Marta,
Okay.
for such a nice talk and interesting discussion. So thank you very much, and thank you all to the public, wherever you are.
See you in person sometime soon.
Yes, I hope so. I hope. I mean, we will really be happy to have you here in person.
Yeah. Good. Thanks again, and have a good rest of the day.
You too.
Thank you.